For those of you listening to this, you've just missed 10 minutes of me speaking at the start. So basically, we've identified all of the peaks. Now, each of those peaks, the relative intensity of them corresponds to the number of atoms which are present in the surface. So each peak is proportional to the number of atoms of carbon, the number of atoms of oxygen. And so what we want to do, of course, we want to use those peaks to quantify the carbon, to quantify the oxygen. But what you'll notice is where we had these peaks, but we also have this significant background which forms after each peak. So on the right-hand side, you have quite a flat, low background, but after each peak, we have this relatively significant background that increases in intensity after each peak. And that background is formed by, for example, carbon 1s electrons being inelastically scattered on the way out of the surface, or O1s electrons being inelastically scattered on the way out of the surface. And so before we quantify these peaks, we have to take account of these backgrounds. And it's quite straightforward. So bottom left of the screen, you'll see we have this arrangement of various cursors. And we also have this zoom magnifying glass, quite useful. So double cursors, one that says select a range on the x-axis, click on that. You'll see we get two cursors appearing, which you can move around. Let's put them roughly where we want to add a peak for the carbon. And then let's zoom in on the carbon peak. And what you want to do here is put your start and end cursors basically before the peak and after the peak. And then at the top on the analysis tab, there's a button here which says peak add. So click on peak add. And it brings up another dialog which has kind of two parts to it, really. The top portion is about the choice of background. So you see here, for example, it's flat on the right, then we have a background on the left. What we want to do is add a background which somehow interpolates what the shape of the background is underneath the peak. And without discussing it too strongly just at the moment, the easiest shape to use is called smart. So select smart background. In the box at the bottom where it says name, we just identified it manually as a carbon 1s peak. Type in C1s, click add. And you can see it adds this green line here. So basically that's interpolated the background shape under the peak. And now what the software does, it integrates the peak above that green line. So everything above that green line and under the red line is now called a peak area, basically. And you'll see at the top left, we now have an entry in the peak table, the quantification table. So C1s was the name we gave it, and you see it has an area. And at the moment, because we've only added one peak, it says it's 100% atomic. That's because we only have one peak at the moment. On the bottom, we see the magnifying glass. I can cancel the zoom. I can move those cursors along to the O1s peak. Let's zoom in again. And again, we want to put our cursor before and after the peak. Smart background, change the name to O1s. Click add. And now you'll see a second peak appears in the table. So we've got C1s and O1s now. with different areas. Now, just going to close the peak adding dialog at the moment and zoom back out. So at the moment, we see the atomic percent column, 72%, 28%. Now, if you look at the molecular formula for PET, then from memory, I think that's pretty much bang on. I think it should have something like 27 or 28% carbon, oxygen rather. So for polymers, you should expect, so you've got carbon, oxygen, nitrogen, fluorine in polymers, then you should expect that the quantification that you get is actually quite close to reality. Assuming there's no contamination on the surface and no modification. So if you put, you know, a perfect, a clean polymer with an extra K alpha, you should get a quantification that's very close to the expected. Now, in this white area at the top, if I use the right mouse button, right click, and say show all columns, that shows you all of the information about the data. And the column I was wanting to focus on here was one which is called an SF, which means sensitivity factor. And that basically is related to this efficiency of photoionization. And you see under it, it says SF AL Thermo 1. And this is a library of sensitivity factors, a library of efficiency factors, which we created at Thermo Fisher. By default, the carbon 1s factor is 1. And you see here that the oxygen 1s factor is 2.9. So what that means is that the O1s photoionization is 2.9 times more efficient than the carbon photoionization. And it's these numbers here which are used to normalize the intensity. So you measure a particular area of this peak, that's a raw area. And in the table, that's area brackets P. That's the raw area. Then you have an area N next to it, that's normalized. So basically, you take the raw area, you divide it by the sensitivity factor, you divide it by a couple of other numbers, and you end up with this normalized area. And then the ratio of these areas, normalized areas, that's what goes to make the atomic percent. So the atomic percent is just a ratio of normalized areas. And the thing to remember, of course, is with aluminium K alpha XPS, your typical sampling depth, most of your information comes from the top 3 to 5 nanometers of the surface. The total sampling depth depends on the exact composition of the material, but the total sampling depth is of the order of between 10 and 15 nanometers. So if you put a bit of PET in, you take the spectrum, the whole spectrum is information down to about 15 or so nanometers. And therefore, the quantification, of course, is for that depth. So one of the biggest questions you'll have is, if ever you're using multiple techniques to analyze your sample, then you need to consider the different sampling depths, of course. So EDX, for example, might give you composition information, which is microns down into the surface, whereas XPS is 10 nanometers. So that's always something to bear in mind. Okay, so there we go. So we've taken a survey spectrum, we've identified the elements, and we basically got a quantification. Any questions so far?
Nope, we're good.
Very good. Okay, so that's a fully manual process, and it can be good practice, I think, to do quite a few manual IDs quantifications. Just kind of gives you an idea as to what's going on and how these things are derived. Let's go back to the beginning here. Let's just add in a peak on the carbon. So we set our double cursors before and after. Analysis tab, and then peak add. So you remember we had a choice of backgrounds here, and I said just use the smart one. So in 9 times out of 10, use the smart background and you'll be okay. Just to kind of point out what the other backgrounds do. So the first one on the right-hand side, simple. Basically, you could ignore that one completely. So the simple background is used on a different machine for a different purpose. So the simple background you can always ignore. For most cases, like adding a peak to a survey spectrum here, background to survey, the Shirley background and the smart background are basically the same. The Shirley background and the smart are basically the same. So if I had a smart background here, CNS, you see the green line. If I now add another background, the Shirley background, and add that, you'll see it's basically the same. So what's the point of having the Shirley and the smart? I'm just going to label this one Shirley and smart. So you see, if you click on these boxes, you can actually add, once you've got your XPS label, you can add other words after it. So if I click on my C1S Shirley, you'll see these little squares appear on the markers. I can now move the background left and right and change it. That's a Shirley background. Now, if ever the background, the green background, goes above the data, well, that's an incorrect background. So you'll see here with a Shirley, if I move it to the left, I can get wrong backgrounds. I can get bad backgrounds. And so I have to move it down here to get good background. Let's look at the smart background that I added. If I click on the smart background, if I now move the endpoint for the smart background to the same location, you'll see that the smart background never goes above the data. So smart background only follows the data. So the smart background just enables you to not be so precise with the background positions. The smart background is smart enough not to cut through the data. So that's why the smart is so good. And the linear background is another one you might want to use. So basically, if you have a big step, then often the Shirley or the smart background is better. If you have quite a shallow step here, then the linear can be useful as well. The question, of course, that then comes up is, what do you mean by big and shallow, big and small? And we'll come to look at that in a bit more detail when we look at the high resolution data. But to be honest, there's no wrong or right here. But like I say, using the smart background most of the time works best. The other choice, as you'll see, is something called a two-guard background. Now, two-guard backgrounds are, so the smart background and the linear with Shirley actually have no physical basis whatsoever. If you had a smart background here, it looks quite reasonable, like a nice step. But a Shirley smart background is actually just a mathematical function which has no physical basis whatsoever. The two-guard background is the only background that has any physical basis. But the problem is the two-guard background is really hard to use, and it actually means you have to collect more data than you normally do with XPS. And then you have to spend a long time doing it. So if you're doing your PhD in silicon oxide and you want to fit this and quantify the backgrounds correctly, then fine, 2-guard background could be useful. If you're analyzing lots of samples every day, or you're using XPS just as a part of a material science project where you're also using SEMs and Raman, etc., and you're not particularly interested in the physics of your background, then the 2-guard is just too much hard work, and you're better off just using a smart background, even though the physics of the background isn't particularly well developed. So 9 times out of 10, just use a smart background. Okay, that's a fully manual bit of processing. But you'll be pleased to know we have an automated routine for this. Let's open up the MICA survey here. So go to your data folder, level 1, and then double click on the MICA survey. What we see here is quite a complex survey spectrum. And we don't necessarily want to go through the fuss and the bother of analysing all of those peaks manually. But thankfully, the software has some tools which will do the job for you. So on your analysis tab, you may well have, there are two buttons which can do an automatic survey analysis. One of them is called Survey ID, and one of them is called ESP. So let's start with the Survey ID. So the Survey ID uses a pattern matching algorithm to best identify the elements present in the survey, and then also quantifies those elements for you as well. So when we press the Survey ID button, it will go through various processes, and at the end, you'll have a survey spectrum with the elements identified and also quantified. So let's go ahead and press that button. Okay, so what we end up here is with labeled spectra, and we also have a peak table, a quantification table. So what you'll notice, for example, in my example here, is that some of the peaks are labeled, but some of them are not. That's actually a preference in the software. So you can either ask the software to label all of these peaks, because some of them are secondary. So for example, this peak on the right here is labeled AL2P. This peak in the middle, just here, is also an aluminium peak, the aluminium 2S. I prefer only to have the primary one labeled in Avantage, but there is an option which allows you to have all of the peaks identified. I think that's in the preferences. Go to edit preferences. Processing preferences, analysis, survey ID. There we go. So show other peaks and show minor peaks and OJ peaks. That will then automatically add in the other peaks as well. The way I tend to like working is do this automatic ID, then go to manual, and then you can basically, okay, it says we have aluminium, click on aluminium, yep, that's both peaks. It says we have silicon, click on silicon, and so on, and then you can work out what you've got that way. So the silicon and aluminium, that's pretty, we're pretty confident about that. The peaks are in the correct position, the relative intensities are correct, and also we have the secondary peaks, which give us some information. In cases like here, though, we have sodium and magnesium. These are very small peaks. So firstly, they're very small, and secondly, because they're so small, we may not have the secondary confirming peaks. And in that case, the software puts these question marks next to it. And basically what the question marks mean is go and have a look yourself. So we open up the manual ID. We click on sodium, for example. We zoom in here. Okay, yes, the peak is at pretty much the correct energy. Also, if you go to the sodium OJ locations, you can see that we have a little peak at the sodium OJ as well. So the software has indicated that the sodium is a maybe peak. We've used a manual ID to confirm that yes, it is a peak, so we can simply delete those question marks, delete those question marks. And then we end up with a quantification table. So you see here the magnesium and the sodium are reasonably low concentration, about 0.5 atomic percent. So with the next-gen K alpha, you should the detectability limits. It varies for different elements, but you should be able to see something like 0.05, 0.02 atomic percent of elements. So if you have really low concentrations, down to 0.02 atomic percent should be possible to detect. So that's an automatic ID and quantification, so really easy. And if the auto ID misses any peaks, then you can simply use the process that I just showed you, and you can then, so you do the automatic ID, and then you can do the manual ID and add in the peaks yourself as well. Similarly, if it incorrectly identifies anything, let's imagine that it incorrectly identified the sodium. I can select the sodium peak, right click, delete selected peak, and it gets rid of it. So the automatic ID is not supposed to be press a button and forget about it. The idea of it is that you press the button, the software suggests what the ID is, and then you should double check it yourself using the manual ID process. So the survey ID that I just showed you is, as I mentioned, is a pattern matching. This presents a problem for the ever increasingly popular element lithium or boron. So lithium only has one peak, the lithium 1s peak. There are no confirmatory peaks. And so the pattern matching algorithm does not work. So survey ID will never find lithium, it will never find boron. So if your samples have those elements in it, then the survey ID will never find it. So you could either press survey ID and add the lithium yourself, or we have another automatic peak routine called ESP. Now this sample doesn't have lithium in it, but ESP can find lithium and ESP can find boron. And it works in some respects similarly to what we just saw, but in a big respect, it has a difference. So we'll just see it. So here's our survey spectrum, analysis tab, and we click on ESP. Now, if you ever find that your icons are missing, just click the button at the end there, which is toolbar options, and then you can basically these checkboxes turn on and turn off the icons. So if ESP, for example, is missing, you can turn your enhanced survey ID on and off. So click on your survey, press ESP. So this time it opens up a periodic table. And what happens now is it does a similar routine to survey ID. And the elements which are green, those are the ones that the software is confident about. The ones in pink are the ones which the software may have found. And you see here in the legend here, pink means not quantified, low confidence. So it's suggested that we've got titanium, perhaps. There definitely is no titanium. And what you can do then, titanium should appear, for example, at about 450 EV. There's nothing there. It's not there. But with a pink, if, for example, you looked at it, okay, there is titanium. If you click on that, it will turn green. Click again, it will turn off, and so on. Click on green, and then click reanalyze. It basically forces the software to find titanium. So ESP, Enhanced Survey ID, is giving you the chance to modify what is found. And when you're happy with everything, click on close. And you can see here we have a peak table now, just as before. You can also see ESP is added in a lot more information as well. Some of it which is overlapping, which is hard to see. So either button is a good start. So if you have a survey spectrum, do the auto ID first, just to get you started, and then go ahead and do the manual check, just to make sure that the auto ID has got it right. Don't ever trust them fully. You ought to make sure that you've inspected the data yourself to make sure. Any questions so far?
Nope, we're good.
Okay.
Hold on a sec. Yeah, go ahead.
Yeah.
Talking about the detection limit and what is the quantification limit? So the detection limit is saying is around 0.2%, quantification limit is percent.
Could you hear that?
Sorry, James, I couldn't quite hear that.
Is there a difference between the detection limit and a quantification limit? So can you be more confident in the detection versus, say, quantification of an element?
Well, yeah, that's a good question. Obviously, if you have a very weak peak, then the errors, if you like, associated with the quantification are going to be greater than a strong peak. But the ultimate quantification limit is the same as a detection limit.
Okay, thank you.
Okay.
Okay, let's just go back to PET.
Oh, I have another question.
Actually, one more question, Paul.
Yep.
Just now for my car data, when we use survey ID, actually the program doesn't pick out carbon peak. Then we go to ESP, it does pick out the carbon peak. So why do we need to use the survey ID? Why not just go to ESP all the time?
Greg was asking that they often get a lot better results with ESP. Is there a reason why you would typically use the other survey ID, automatic survey ID for things?
I tend to use survey ID mainly because it does it in one go, and then I can do the manual ID. And it also gives me less information. I find the ESP can be a little bit overwhelming sometimes in the information it gives. So that's the only reason why. If you're happy with ESP, then go ahead and continue using it. No problem at all.
Okay.
Okay, so that's the survey. So surveys, of course, give you elemental composition information. What we're going to do now with the PET is start looking at the high resolution data. So go to File, Open, and then in the data folder, look in Level 2, and then PET regions. And so what we've done here, of course, is the survey spectrum is collected under conditions of high sensitivity but low energy resolution. And this is set by something called parse energy. So when you're acquiring the data, you may see a box on the screen which says parse energy. Basically, a high number means the energy resolution is poor, but the sensitivity is very good. A low number means that the sensitivity is not so good, but the energy resolution is much better. So a survey spectrum is collected at pass energy 200. How would you check that? So if you, on any spectrum, if you select your spectrum, and then where it says display modes, there's a button that says I. Click on I, and it basically all of the meta information about the data is stored with the data. So if we scroll down in the meta information here, it says CAE pass energy 100 EV. So normally on a K alpha or Nexa, you probably acquire your surveys at maybe 150 or 200 EV. So that's a high pass energy, high sensitivity, which is good for looking for low concentration elements. If we look at the carbon 1s scan, the right-hand side here, and do the same, you can see that the pass energy here was 25 EV. Now, on a Nexa K alpha, typically you'll use a pass energy 50, I imagine, to get most of your high resolution data, and that's okay as well. So what are we doing here? If we zoom in on the survey peak, so the carbon peak on the left in the survey and the carbon spectrum on the right, that's the same photoionization. It's the same X-ray in, photon electrons out. The spectrum on the left is collected under conditions of low resolution, and the spectrum on the right under conditions of high resolution. The step size on the left is 1 EV. So each of these points corresponds to 1 electron volt difference. On the right-hand side, each of those steps is 0.1 EV. So the high resolution data has a lower pass energy, but also the step size is smaller. So in a survey, we're looking really just for the overall peak intensity. In the high resolution data, we're now interested in the individual peaks themselves. So all on the right-hand side here, let's just make that bigger again. So with the high resolution data, all of the intensity here is due to carbon 1s. So all of these electrons have come from the carbon 1s level. But this is where the real power of XPS is, of course, in that carbon atoms in different chemical environments now have a subtly different energy. So the peak on the right here, and the peak in the middle, and the peak on the left, all come from carbon atoms, but they come from carbon atoms in different environments, different chemical states, as we say, different oxidation states. This is where the real skill and most of the difficulty comes in with XPS. Processing the survey spectrum, as we've just seen, is quite trivial. Processing the high resolution data to understand the chemistry, that is the real skill of XPS. And this is where you get the most benefits from XPS, but also where often you can get the worst results. And there's lots of talk at the moment in the XPS community about the quality of peak fitting and data interpretation in the literature. So making sure you get your peak fitting the best you can is a good thing. Now we're beginning with a really easy example. When we peak fit this, you'll wonder what all the fuss is about because it's so easy. But then we'll look at some that are a bit more complex. What I would say is peak fitting initially can look quite daunting, quite complicated. But I've been doing this for over 20 years now, and basically, you always use the same process. When you peak fit, if you use the same process every time, it'll stop you making too many mistakes. So, how do we start to peak fit our high resolution data? So again, bottom left, we have our double cursor, and that's where we set the start and end. And then we go to on the analysis tab, the peak fit button. And what it does, first of all, it puts this triple cursor at the highest point of the spectrum. So we get this dialog come up, which is the top half of it is very similar to what we just saw for just adding a background. So again, you have a choice of backgrounds. Again, smart background is the easiest one to go for. So what's the point of this three-pronged cursor? So you can basically change the width of that. And what you want to do is make the width of it roughly, only very roughly, the same width as a peak you want to add. So we set our cursor where we want to add a peak. And I'm going to add, there's a button here that says add single peak. So you click on that and it adds a peak. At the moment, all we've done is added a peak. We haven't fitted. So that's why that blue line is now so far away from the red one. Now, when I click add single peak, you'll notice that the triple cursor moved all the way to the left. Which just happens, so basically at the top here, you see this blue line? That's the chi-square. That's showing where at the moment the biggest misfit is. So that triple cursor just automatically keeps on moving to the maximum error. But it's actually, when you're doing peak fitting with XPS, it's more useful to work from the right to the left. So we added a peak on the right. The next one we should add is this one in the middle. Add single peak. Now, why is it easy? Why is it better to work from the right to the left? So if you go to the peak fit table, top left, you go to what's called the peak fit table. Every time I'm pressing add single peak, it's adding an entry into this peak fit table. And again, if I go to this last peak, I click add peak, you'll see it adds another. But at the moment, I've added three components, and I've got 3 components in my peak fit table. So at the moment, what I could now do, I could go to this tab on my dialog, which is Fit Peaks, click Fit Peaks, and I can click the button which says Fit this level. Fit level, and there we go. You can see that those 3 components have fitted quite nicely. On the left-hand side here, you can see we've got an area of a spectrum which has not been fitted. So let me just move that cursor over again. It's quite broad, so to broad down my cursors, click back to the Add Fitted Peak tab, click Add Single Peak, fit this level, job done. So you see we have quite a reasonable fit. So if you look at just PET, you could wonder what the fuss is about. This is very easy so far. We have 4 components now. One of the harder bits now is we have to try and label what these peaks are. Now this is PET, so it's quite easy to work out what they are. The peak on the right is just carbon-carbon. So typically, not always, but typically, if you have a peak around 285 or just under, well, that's either aliphatic carbon, so single bond, say C single bond carbon, or aromatic carbon, like here, we have like a phenyl group or benzene ring. The next one along, that's due to ether carbon, so like COC. The next one, that's your ester. It's like C double bond O sort of thing. And then the last one is a satellite feature. We won't talk about too much about that just yet. So we've got three peaks. We've labeled them what the chemistry is. If I now click OK, and go back to the peak table where it says peaks, you can now see that I've added those components into the quantification table. So what we actually have now is we've literally quantified each of those individual chemical states. Okay, so that's for the carbon. And then we have the oxygen to do as well. So again, double cursor, before and after. Press the peak fit button on the analysis tab. Add single peak, add single peak. In our peak fit table, we have two components here. Click fit peaks, fitness level, and OK. Oh, I've got to change the name. That's COC. That's CO. And what we have now is we have a quantification table with carbon and oxygen in it. And this time, not just the elements quantified, we've actually quantified the individual chemical states. So if you were to draw out a PET molecule and counted up the atoms in the phenyl ring versus the atoms in ether groups versus the atoms in carboxyl groups, you would find that the ratio actually matches this quantification extremely well. Oh, that's wrong. That should be carboxyl. So what we see here, for example, is carbon 1s in ether groups, 15%, and for PET, oxygen 1s, 15% as well. Similarly, carboxyl oxygen, 11%, carboxyl carbon, 12%. So match very well. That's not always going to be the case, of course, but for PET it is. So PET is very easy to peak fit. Why do I say that? Well, we can see the individual peaks. So on the carbon spectrum, we can see the big peak, we can see the middle peak, we can see the carboxyl peak. There's no question at all how many peaks we have. We have 3 peaks in the carbon, we have 2 peaks in the oxygen. It's really quite straightforward. The difficulty with XPS peak fitting comes when you can't quite see how many components you have, or you can't quite see what the relative widths or the relative shapes of the peak should be. So let's have a look at an example of that. So if you click on your oxygen spectrum and right mouse click, you should bring up a dialog which says show XPS knowledge for this spectrum. And if you click on that, it opens up the knowledge base. So this knowledge view has lots of information about all sorts of elements and all sorts of useful information about acquiring data and processing your data. What you'll see is that some of these spectra of the knowledge base have a blue box around it. And in a minute, we'll click on that blue box and it will open up the raw data for us. But this example here shows this is a real difficulty with peak fitting. So we have an O1S spectrum here from copper carbonate. And if you forget about the blue and the red lines at the moment, just focus on the black raw data, you can see that we have a peak which has an asymmetric shape. So that tells us that we should have more than one chemical state. But it's only an asymmetry. We can't see those 2 peaks clearly. there's only a shoulder. And so here, as it shows in the knowledge base, you could peak fit this data in 2 different ways. And you would end up with completely different ratios of carbonate to hydroxide. So over here on the left, the ratio of carbonate to hydroxide is 4. On the right, the ratio is 2.5. Which one is true? The problem is with XPS, in this particular case, you don't know. So this is the real skill of XPS, is when you have data like this, where things are not clear, how can you process the data in the most appropriate way? So if you are processing this data to publish in a paper, how should you process it such that the referee doesn't write back to you saying that you completely mucked up peak fitting and it's all nonsense and meaningless? So this is where having a fixed routine for peak fitting is helpful. So if we click on this dialog now, if you click on these spectra, it opens up the raw data. So what we're going to try and do now is peak fit this option spectrum in the most responsible way we can. So you'll see at the moment we have 2 peaks. I'm going to delete those. So go up to your peak table. In that box at the top left, click on that, and then right click, say delete all peaks. That gets rid of the existing peaks.
If you have the,
Okay. So let's imagine we're brand new to the spectrum. How do we go about peak fitting this? So as I say, one of the things to remember with peak fitting XPS data is you're not necessarily looking for the truth. What you're looking for here is to process the data, to peak fit the data in a way that is responsible, in a way that is consistent with the data, and in a way that is physically meaningful. Obviously, what we could do here, we could fit 10 components to the spectrum, and we'd have a wonderful fit, but it would be meaningless. So what you're trying to do when you peak fit, you're trying to make sure that every component that you add, you can defend it. If somebody says to you, why have you added that component, you can tell them why you've done it. So when you're peak fitting, remember your target is not the truth. Your target is scientifically reasonable. Okay, double cursor, again at the start and the end. And we're going to go peak fit. So the best thing to do is, okay, let's begin just by trying to add 1 component. The simplest fit would be 1 peak. So add 1 peak. Go to the fit button, press fit this level. Okay, so it's clear that adding 1 peak is not a good fit. You've got these terrible misfits. So there's definitely more than 1 component. That's fine. Okay, go to the peak fit table again, peak fit tab. Now, if you click where it says A on the left-hand side, you'll see these little boxes again appear on your peak, and you can drag it around now. So you can drag it, you can change the width. So I'm going to put that peak on the right. I'm going to go back to the peak fit dialog and say add fitted peak. And I'm going to add another peak to the left. So click add single peak. And we've added another component here. So we've got O1S scan A, O1S scan B. So the question now is, okay, well, I've got 2 components. What are their relative widths? What are their relative shapes? There are two parameters which tell us this. So one of those parameters is the FWHM. That's forward half maximum. So that's how wide a peak is. And the other one is this thing where it says LG mix. So LG mix just means Lorentzian Gaussian mix. So basically, an XPS peak has quite a complex shape, but you can simulate that shape as a mixture of Lorentzian and Gaussian functions. Basically, if it's more Lorentzian, it means the tails on the left and the right, the tails are bigger, that's all. So the best way that I would recommend fitting the data is, you've added two components. The best way always of fitting data, if you cannot see clearly what those peak shapes are, like a PET, you should always begin by fixing as much as you can. What do I mean by fixing? So we've got two components here. The best way of peak fitting is to make sure, to begin with, that their widths are the same and that the LG values are the same. And that's your first attempt at peak fitting. So how do we do that? How do we make the width the same? And how do we make the LG the same? So you'll notice here in bold, so underneath, so you have a row here which is A, O1S scan A, and you have all these numbers, and then underneath you have another row. Those rows underneath are called the constraints, and this is where we can start to build these relationships between peaks and components. So what we're going to do here, I want to say, okay, component B, the one on the left, I want that to have the same 4.5 maximum as component A. So I click here for component B and I type A times 1, enter. And what that means is that at the moment, component A, the width, can vary between 0.5 and 3.5, but component B must always be the same width as component A. Similarly, in the LG column, I can do A times 1. And that means the LG for A can vary between 0 and 100. But the LG for B should be the same as A. Now, what you might find is on your software at the moment, in the LG column, does it say 30 with a padlock next to it? If it says 30 with a padlock next to it, go to Edit, Preferences, and then Processing Preferences, Analysis, Peak Fit, and if it says LG ratio 30 and then fixed, where it says fixed, delete that and type 0:100 instead. And that means that next time when you try to do peak fitting, you'll have an LG value which can vary from 0 to 100. Fixing it at 30 is not a good idea. Okay, so at the moment, component A is going to vary, but component B is going to have the same width and shape as the other one. So we're going to fit. Yeah, go ahead. Is there a question?
No.
Okay. Go to the Fit Peaks tab, press Fit this level. And you can see we've got a pretty good fit. So as we saw in the knowledge base, though, it is possible to fit the spectrum in different ways with different widths. But what we're saying here is the resolution of this peak is not good enough to give you the information about the relative shapes, the relative width. So by using this procedure, where initially you try and fix as much as possible, this procedure stops you fitting inappropriately. It stops you trying to allow too much variation in your peak fit. So you should always begin by fixing as much as possible. But what we see here on the right-hand side of this the fit here is not great. So what we want to do now is we could add another component, but then we're adding, as I say, adding more and more components, you'll always get a better fit. The best thing to do is, at the moment, we've constrained everything to be the same. What we can now do instead, we can say to the software, okay, I quite like this peak fit, but I just want to allow the software to relax it a little bit. So in each of these dialogues, with a peak width, I can say plus minus 0.1, plus minus 0.1. And that will allow the width to change just a little bit for each of those components. So click fit. Still not great on that one. Let's try doing plus minus 0.2. Not so bad. So the general approach, and this is the approach which I use in all peak fits. To begin with, link all of your components together, make sure they're as similar as possible, and then allow them to relax a little bit. Once you've allowed them to relax a little bit, if you still get a poor fit, then add another component. But go back to the beginning where you make them all the same width and shape again. So always use that approach and it'll stop you going too far on with peak fitting. Now, what we'll do now, we'll have a 10-minute break and then we'll come back and we'll do some more peak fitting so we can kind of reiterate what we've looked at here. Are there any questions about what I've shown you on the peak fitting before the break?
Yeah.
Question, is there a physical argument on why the peak should be the same width?
Is there a physical reason why the peak should be the same width?
Yes and unfortunately, yes and no. That's a good question. Now, broadly speaking, again, it's not always true, but let's say, for example, you're looking at a polymer like PET. The components from a single region are generally similar widths. They're not always the same, but generally speaking, they're similar. So if you look at the carbon peaks here, where we did not fix them, you'll see the first peak is 1.02, the second peak is 1.14, the third peak is a little bit different, 0.84. But what you don't see one peak being 3 volts wide and one peak being half a volt wide. So when you're looking at a particular region, your peak should be a similar width. So fixing them to begin with and then allowing them to relax just allows you not to end up with one very broad and one very thin peak. There are some cases where the peaks should be different. So, for example, if you look at oxides versus metal, for example, I'll find a good example. Nickel, here we are. So look at nickel. So nickel metal, for example, the peak is quite narrow, and the oxide and the hydroxide is quite broad. So metallic peaks are quite narrow, and oxide ones are broader. But generally speaking, within a particular region, you should aim to have the peaks as a similar kind of width. If that answers your question.
Yes, thank you.
Yep. Okay, we'll take a quick 10-minute break. Paul, I'm going to stop the recording and then I'll restart later and get to recordings, make that smaller file. We're back in 10 minutes.
Okay, so we'll be back at what, 25.2?
Yes.
Cool.
Alrighty. We are now being watched by the all-seeing eye of Microsoft.
Okay, so we're going to get back to the knowledge view that you should have open. If you don't have it open, just as I say, go to one of like the O1S spectra that we've got, or any spectrum we have open, right click and say show XPS knowledge for this spectrum. And then top left, there's a little periodic table. You want to click on sulfur. Everyone's okay with that? And it's nice these couple of S2P sulfur spectra here. We're going to click on that blue box. And it's going to open up this sulfur spectrum. Does everyone manage to do that? Okay. Right, so delete those peaks again. Okay, so this is a sulfur spectrum from a more complex compound. And we're going to use exactly the same rules that we used just now about linking shapes and linking widths. But there's an added complication. So what you may have seen already in your work is that if we go back to the O1S for PET, for example, we see two components that corresponds to two different chemical states. But in some cases, like with sulfur here on the right-hand side, this is tungsten sulfide. So it's only one chemical state. But in the sulfur spectrum, we see two peaks. So if you have an s orbital, O1s, carbon 1s, then for every peak, every component that you see, that corresponds to one chemical state. But if you have a P, a D, or an F, gold 4F, silicon 2P, sulfur 2P, if you have a P, D, or an F, you have this effect called spin orbit splitting. And what that means that now, if you have one chemical state, you have two peaks. So this is a physics effect, not chemical information. So what you end up with P, D, or F peaks is this splitting into doublets. And again, the knowledge base has information about this sort of thing. So make sure you don't accidentally think you've got two chemical states here for the sulfide when you actually only have one chemical state. So this is something that's very important, but it's something that software helps you with. And as I say, the knowledge base can help you with it, but also when we come to the peak fitting, it can help you with it as well. And that's what we're going to look about now. So you see here, for example, tungsten sulfide on the right. So that's one chemical state. We have two peaks. On the left-hand side, we have sodium sulfite and sodium sulfate. So we have two different chemical states, and we end up with four components. So you get that doubling. So let's get back to our peak then that we opened up. So again, we start the same way. We put our cursor, a double cursor at the start and the end. And we go to the peak fit button. So the software helps you here because the spectrum is labeled S2P scan, the software picks up this label and it puts it in this box here. And because it's P, D, or F, now we can say add doublet. So if I click add doublet, instead of adding just one component like we did before, it adds doublet. So if we go to peak fit table, you can see that it's added two components. But you'll notice something, that these constraints have been added automatically. So when I click add doublet, it adds 2 components, but it automatically adds in these constraints. What are these constraints? So I mentioned that this doublet is an effect called spin orbit doubling. What that means is that you have 2 components, but the separation of each peak and the relative intensity and the relative width is a physical characteristic. So what's happened here is when I click add doublet, the software added 2 components, but it automatically said those 2 components must be separated by 1.2 EV plus or minus 0.1. It said that the relative height of each of those components should be 0.511. And it said that the width of the components should be the same. So when you click add doublet on peak fitting dialog, it automatically adds in these 2 components with these fixed constraints. So you'll come across this a lot in your XPS work, this spin orbit doubling. And so you'll need to use the add doublet feature quite a lot. So you can see quite clearly we have 1 pair of doublets on the right, but on the left-hand side, there's definitely some extra intensity where we need to put some more peaks. So click the reset markers button if you need to. I can now move that across, and you'll see the add doublet actually has grayed out. It's because I've moved too far across. If you move it back a little bit, there we go, it comes back on. Click add doublet again, and now it adds another doublet. So it looks as if we have 4 components here, and we do, of course. But in terms of the relative behavior, we only have 2 chemical states, and we've got 2 sets of doublets. So if you look carefully, you'll see here row A. With row A, the peak end, the binding energy can vary however it likes. The height can vary however it likes. The width must vary between 0.5 and 3.5. But basically, this first component, when I press fit, that first component can do whatever it likes. But the second component B, which is a spin orbit component, must behave according to these constraints. But at the moment, component C can also do what it's like, do what it likes. So at the moment, if I press fit this level, then component C, which is this third peak here, its width can do whatever it likes. Similarly, component A, the width can do whatever it likes. But what we want to do is use the rules we learned before the break, where we try and fix as much as possible. So component C, I'm going to type A times 1 in the width, and the LG A times 1. So what that means is the 4.5 maximum of this little component here at 169 EV must be the same as this bigger one on the right. And the LG value of this little component on the left must be the same as that on the right. So click fit. And you can see, even with these constraints, we've got quite a good fit. And if you look at the results here, component C, this little 168.5, has a width of 1.1, which is the same as the component on the right-hand side, a width of 1.1. So even though the spectrum is more complex, we're using the same procedure, which is basically fix as much as possible, fix the widths to be the same as all of these 4 peaks have the same width. All of these 4 peaks have the same LG, and you end up with a good fit. And the ones on the right are sulfite. And the ones on the left are sulfate. And OK. Now, when we go back to the main quantification table, you can see something interesting has happened. So we have 2 sulfite peaks and 2 sulfate peaks, but only one of each is quantified. So when you have this spin orbit doubling and you peak fit, you normally only quantify from the biggest peak. So that's S2P3 here. And you see we have in the Q column, we have a tick. The smaller peak, S2P1 sulfite, says 0% and does not have a tick. So basically what this is, when you peak fit a spin orbit doublet, the sensitivity factors for each peak, you only have to quantify from one component, and we normally do the biggest. If you clicked both of them, you're basically double counting. So you end up with 91% total, when it should be 84%. So if you peak fit spin orbit spectra, only quantify from the biggest number. When you use the add doublet function, the software does that for you. So if you go back to the beginning, the software does it all for you, actually. It's quite nice. So we do peak fit, add doublet, add doublet. We simply make the width the same, the LG the same, 8 times 1, 8 times 1, bit peaks. When you press OK and go back to the peak table, it automatically turns off the peaks that you don't want to quantify. So the software really makes it very easy for you by doing that. So it's definitely a more complicated spectrum, but by using our approach of making where it's not clear, you make everything the same width, then it makes life a lot easier. Now, having said that, the next example is one where the resolution is much better and you can use a different approach. So if you go to File, Open, and then in Data Level 2, you want Si2P native oxide. So what you have here is, this is a very simple silicon wafer piece with a native oxide on the surface. So what we see here, it's silicon 2P. So it's 2P, so you're expecting there to be spin orbit splitting. And it looks like we have 2 chemical states, of course. The elemental silicon from the wafer and the oxide on the surface. But just by looking at the spectrum, we can see they look, each part of the spectrum looks quite different. On the right-hand side, we can see this very well resolved splitting. And on the left-hand side, we can't. We can only see a single peak. So what's happening here? So let's go ahead and peak fit. Put our cursors on, start and end. And then peak fit. And then add doublet. And again, on the broad thing, add doublet. Now, in this case, it would be silly to make the widths the same, because we can see quite clearly just by eye that the peak's shape and width on the right-hand side is completely different to peak shape and width on the left-hand side. So we've added a doublet on the right and a doublet on the left. Going to fit peaks, fit this level. And what we see here is the broad peak on the left looks okay. But on the right-hand side, it's a very bad fit. So if we go to our peak table here, at the top, we can see here it says 4.5 maximum, the limit is 0.5 to 3.5. And obviously what's happened here is the data in red is actually narrower than 0.5 EV. So click on the 0.5, 3.5 bit. And on the right-hand side, we have a padlock with a cross through it. Click that, and it turns off that constraint. Press a padlock, it fixes it. Turn it off, it unfixes it. With it unfixed, we can now click fit this level again. And now you can see we get a pretty good fit. So the stuff on the right is just elemental silicon. And the stuff on the left is oxide. Click OK. And again, only the 2p3 is quantified. So we have a tick where it says Si2p3 elemental, and we have a tick where it says Si2p3 oxide. On the right-hand side, we can clearly see the spin orbit splitting. On the left-hand side, we can't. And if we look at why is that? Well, if we look at the 4.5 maximum column, now this is what I mentioned earlier, with metals or elemental, they can be quite different widths to the oxide. So the width of the elemental is 0.34 EV. The width of the oxide is 1.35 EV. So the oxide, the actual width is so broad, and the splitting is relatively small. So two broad Gaussians add together to make one broad one, basically. So here's something interesting. So at the moment, we fitted the right-hand side with a doublet and the left-hand side with a doublet, and we've got about 24% oxide. So remember that number. So we had Si2p3 oxide, 24%. Let's delete that, start again. So add doublet. Now this time to the oxide, instead of adding a doublet, let's just add a single peak. And again, let's turn off the constraint. They fit that. So the element has a spin orbit doublet in it. The oxide does not. Click OK. go back to our quantification table, and you see again, the oxide says 24%. So even though we fitted it in a completely different way, adding only one peak rather than the doublet, it still says 24%. So why is that? Well, remember before, when we fitted it with the doublet, we called it SI2P3 and SI2P1. The software has particular sensitivity factors for that. So when we have SI2P, the factor is 0.9. Where you have SI2P3, the factor is 0.596. So you can either fit with a doublet or you can fit with a single peak, as long as you get the label correct. And then the software will automatically set the correct factor depending on the label that you give it. So when you're fitting silicon oxide and elemental, you normally just forget about the doublet splitting in the oxide. You just fit it with one peak because it's so broad. But because you change the label from Si2P3 to Si2P, the correct sensitivity factor is picked up and everything works out in the quantification. So either approach is fine, just make sure you use the correct label. And again, in the knowledge base, it gives you information about this. So here, for example, it shows the same thing here, fitting the elemental peak with 2 components and the oxide with 1. And also show you actually the difference. So often when you measure silicon spectra with a higher pass energy, you see an asymmetry, but you can't quite see the spin orbit splitting. Whereas if you use nice low pass energy, you can see that splitting. Okay, but just as another example here, if you go to data level 2, and then lead 4F, other data. So this time we have an F orbital, so lead 4F. So cursors at the start and the end. But again, it looks like quite a complex spectrum, but it's actually quite easy to fit, particularly in this case, as we can see by eye that some peaks are narrow and some peaks are broad. So fit doublet. So again, smart background, but add doublet. And then add doublet. Click fit. And it's come out quite nicely. So fitting these spin orbit doublets doesn't have to be too difficult, as long as you remember, if you can see that they have different widths, that's fine. You don't have to constrain them. But if you can't see them, if you can only see a shoulder, then make sure you use a procedure where you set the widths to be the same. So when you have a P, D, or an F, make sure you use the add doublet function in the peak fitting dialog. So peak fitting, as I say, is probably the question we get asked most about, and it really is the skill. Acquiring data is very easy now with the next and K alpha. The real skill that you bring to it is in the peak fitting, and just make sure that you use a knowledge base and make sure you don't overfit data. Always make sure that you can defend the reason why you're adding a particular component, and you shouldn't go too far wrong. Are there any questions? Well, I'm sure there will be, but are there any questions about peak fitting before we move on?
Looks like we're okay.
Okay. So have any of you tried peak fitting so far? in your own work?
Yeah, people are nodding yes that they have done it before.
And has that gone okay, or have you come across any problems with that?
Occasional problems, but usually okay.
Occasionally a problem, but usually okay.
Okay. Okay, good. Well, in which case then we're ready to move on to level 3. So what should we look at? File, open, data, level 3. So what we've looked at so far is data just from a single point analysis. So you put your sample in and you take data from a single point, and you have your spectra for quantification, for quantifying chemical states. What we're going to do now is look at how to do some simple processing from depth profiles or imaging. So let's look at the imaging folder, and let's go to the folder called PET mapping. So what I'm going to show you here, I wouldn't necessarily try and follow it every step unless you're very fast. It's really more about giving you an idea as to what's possible with your systems and what's possible with the Avantage software. So feel free to follow along step by step, but if you get lost or anything, it's more about giving you a flavor as to what you can do with your system, and give you an idea maybe of some future work you might want to do. So what we have here is an example of some imaging data on a K-alpha. And so we have a polymer, PET, and we just drew the Greek letter alpha on that polymer. And then we have an array of spectra. We had a map. And that map in this case was 5 millimeters by 4 millimeters. And we set up an array of points, X and Y. And at every point in the area, we took a full carbon 1s spectrum. So every pixel in the image, there's a carbon 1s spectrum associated with it. So the first thing to note is how the different ways Avantage allows you to visualize the data. So what we have here is what we call an image stack. So at the moment it says, for example, C1S raw data, and then it says 288.78 EV. So what this means is this is the image that corresponds to a photoelectron energy of 288.78. At the bottom, I can use these arrows to step through the data. So this is the lowest energy, 279.2. As you can see, there's nothing in the image. And I can step through the different energies, and I can see how the image changes. Or in display modes, at the top here, I can click on the E button. And now what we have is this is an individual carbon spectrum from coordinates 2020, 40, 40. And I can step through those coordinates. And you can see how the shape of the carbon spectrum changes. PET, ink, PET. Display modes, press the XY button. There's the image at different energies. So what you've ended up with here is a data cube. You have energy coupled together with X and Y from the image. And of course, you can visualize that data cube from different directions, and that's all we're doing. So how would we go about processing this data? If we press the E button, I can take my double cursors, start and end, analysis tab. I can do peak add a smart background, carbon 1s. Now, when I click add, when I add a background to one spectrum, it automatically adds a background to lots of spectrum. So that's it. So by simply adding in the background, that's all I have to do. So if I had 5 or 6 elements, you would simply add a background to each element, and that would be it. And then on the analysis tab, you go to the icon that says peak table profile. I think in your version, it may look like a waffle. Peak table profile. And then, for example, atomic percent or area, I can click and generate. Now, I can generate a map of the total intensity of the carbon as a function of X and Y. Now, of course, this is PET with ink on it, so there's carbon everywhere. So just by adding a background for the total carbon has not helped at all. What we really want to do is pull out the different chemical states of the carbon. And there are different ways of doing that. So we could, for example, peak fit every single pixel. And that's possible, but it's a little bit difficult and perhaps a little bit beyond today's training. What I'll show you is some very quick, simple ways of analyzing this kind of data that would get you started. So, double cursor, start and end. And then instead of peak add, what we can do is, on the analysis tab, there's a series of buttons here that say NLS, TFA, or PCA. These are all reasonably similar functions. They're like cousins. They're not the same functions, but they're similar. They're related to each other. I'm going to start with one called TFA, Target Factor Analysis. So I press TFA. This dialog comes up, and again, the top part of it is just the same as we looked at already, choice of background. So let's use smart background. The start and end we've already set. The one that's of interest here is one called signal to noise ratio. It defaults to value of 3. For the moment, let's leave it at that, and we'll explain it soon. If you press Start TFA, you can see this white window underneath now has two rows in it. Number 1, number 2, level 188, level 100. Now, when I press Start TFA, it opened up a new grid full of lots of interesting information. The most important bits of information here, top left, TFA levels, level 100, level 188, which are the same as those numbers in that dialog. What does this mean? When we pressed Start TFA, what the software did automatically, what we had, of course, was an array of carbon spectra. We had maybe 200, 250 carbon spectra. The software automatically looked through that data set, and what it says is, I can find 2 carbon spectra, level 100, level 188, and these 2 carbon spectra I can mix together to make all of the other spectra. Every other spectrum in the data set is simply a linear combination of these 2 spectra. So if I click Accept and go back to the raw data, you can now see we have a peak table here, which has got level 188 and level 100 in it. And again, if I go back to by creating a table, normalized area. Now I have an image with an alpha on it, and this image corresponds to level 100, and this another image corresponding to level 188. So level 188, of course, then is the ink carbon spectrum, and level 100 spectrum is PET. So if you go back to that TFA window that opened up, level 100 is the green spectrum, and that looks like PET. Level 188 is the ink spectrum in red. And what this means is every other spectrum, you take a linear combination of those two spectra, and you can fit every other spectrum. So TFA is a way where the software can automatically find a few spectra to fit everything, and then fit the rest of the data set using those few spectra automatically. So what it is, it can be thought of as a way of identifying different chemical areas on the surface, and it finds them for you so you don't have to. So let's go back to the beginning. Shut down that window. TFA. So with a signal to noise ratio of 3, we find two factors. If I turn that down to 1, let's say, now we find 3 factors. So what does that mean? If you look here on the left-hand side, you can see here those 3 factors. The red one is the ink again. The blue and the green ones are both PET, but ever so slightly charge shifted. So if you turn down the signal to noise ratio, what you're allowing is you're allowing more and more of these levels to be added in, and they may only be subtly different. But if you make the value too high, let's say 10, actually it's found no factors. There you go, 5, it's found 1 factor. So if the value is too high, you don't find enough information. If the value is too low, you find too much. So 3 is always a good starting point. And we find 2 factors. We go back to our data set. And now what you can see here is, look, I can step through the data and you can see how it's fitted it using the PET spectrum plus the ink spectrum. And if I go to those different points, you can see there, each spectrum is a linear combination of the ink and the PET. TFA is a really good way of quickly filtering your data to try and understand where the differences are in an image. Now, one of the really cool things you do now is, let's say we create that image. Now, if you created this image on the K-alpha or on the Nexa, if you actually at the system itself and you created this image, you could go to the bottom and go to his cross where it says select point. So click that, and then you can put a point on the image. And when you right click, you could say add point to experiment. So what would happen then is you would add a point here, and then you could go into a survey spectrum or other high resolution data. So by using an image on your K-alpha Nexa, once you've done one image, you can use that image to generate analysis points. So for example, let's imagine you had a sample which was optically invisible. So let's imagine you had, molybdenum disulfide flakes on a silicon wafer. You could not optically see those features, but if you did a map of molybdenum, you could find your flakes of molybdenum sulfide and then say to the software, go to these positions on the and do further analysis. So you can use the image to, like an optical image, and generate analysis positions. Or really nice, if you go to your image, go to the image tab at the top here, click on the image tab, and on the left-hand side, you have an icon, or you should have an icon, which says average spectrum. So click on average spectrum, brings up this dialog. You get a box, which you can resize and drag around. I can now put this box over here on the right and say generate in the dialog. And this is showing me what is the average carbon spectrum within this box. Move the box over here, click generate. This is the average carbon spectrum within this box. So by using this average spectrum dialog, you can actually take your image and then do a small area spectroscopy directly from the image. And that way, that allows you to get really interesting information. So images are not just pictures. They actually contain useful spectroscopic information, which you can then do further processing with afterwards. Okay, that's a very quick demonstration of what you can do with imaging. Are there any questions on that before we move on to the final section about depth profiling?
Question?
Yeah.
If that's okay.
Hmm?
One is, how do you generate the image from your XPS data? How do you get that?
Sure. First, she's asking how you make an image. What's your second question? Because that's a
The second question is, can you batch process data without an image by just pulling up multiple data?
and then she's asking about batch processing data that's not necessarily an image or a depth profile.
Okay, yeah, I've got you. Okay, so the first one. So on the first one, are you asking about how to actually acquire the data in the first place? So let me just show you that. So on your system, your Careful Nexa, there are different ways of doing this. I'll show you the way that we just did for the PET. I'll share that. Let's share. Okay, so to create a map, so normally you have your X-ray and then you have a point. If on the right-hand side, or in the middle rather, you select area, and then press the shift button, like in PowerPoint, shift and then just mouse drag. You could draw an area directly onto the optical image, which you can then resize, for example, or change the number of steps in it. Like so. And then up in the experiment tree where it says area scan, then underneath, you, for example, then just put your carbon and oxygen snapshot data. And the snapshot then acquires very quickly, like so. And then what this would then do is it would go to every point on their area and collect carbon and oxygen data, for example. And then that would be exactly how we generated the data I just showed you. The second part of the question, yes, it is possible. It's probably a little bit beyond the scope of this training session. Maybe the best thing to do would be just to either write a little explanation or point you towards the help file section on that. I could do that via James, if that's okay.
It gets a little trickier when the data is not all exactly the same as it is, exactly the same conditions and setup as it is like an image file or a depth profile setup. It just makes things a little trickier when it's from different scans, different conditions.
Okay, well, just to finish off, this is similar to what we've just done, but just in a different direction. So in your data folder, level 3, depth profiles, let's start off with the 30 nanometer tantalum oxide. So depth profiles and imaging are what we call in the software terminology, multi-level data. So you have spectra either in an XY direction or with depth profiles in the Z direction, going down into the surface. So the actual processing you use is quite similar, even though, of course, you end up with different looking results at the end. So what we have here is a depth profile, which was 30 nanometers of tantalum pentoxide on top of a tantalum substrate. So here's the raw data. So on tantalum, you can see it says you have a single spectrum, and it says H times 0, H level 0. At the bottom, I can step through the H time. So the H time is getting bigger and bigger until we end up with, we're in the substrate, like so. So that's one way of visualizing the data as a single spectrum just by stepping through. Or under display modes, 2D chart shows you all of these spectra with their raw intensity. Or the button next to it, stack chart, that's a normalization. Or a 3D chart, for example. So they're all quite useful ways of visualizing the data. Now, similar to the imaging I showed you, the easiest way to process depth profile data is just for imaging elemental information. So we put the cursor at the start and the end, and we add a background. Click add, like so. And because I've added a background at one etch time, it automatically uses the same background at every different etch time. So just adding a background is really quite simple. Now, for the tantalum, this is why the smart background was invented. This is quite interesting. If we add the background for tantalum here, let's imagine to begin with, we use a Shirley background. Shirley, click add. That works okay. But if we go to the end of the profile with a metal, it looks rubbish. So if you make that good for the metal, okay, it's good for the metal, it's bad for the oxide. So with tantalum, actually, with a linear background or a Shirley background, it just doesn't work. But using a smart background, you can set a background that works in every case. So if you had a smart background, it works for the oxide and it works for the metal. So the smart background is really nice. So all we've done, we've added the backgrounds to each of them, and then we go to our analysis tab, peak table profile, and we can make an atomic percent profile. Job done. So to create elemental profiles is really quite straightforward. Just add your backgrounds, create a profile. Now, the observant among you will notice there's a slight problem here. If you look at the profile, it seems to indicate that at the end of the profile we have about 10% oxygen. Now the substrate is pure tantalum metal, so we should have no oxygen really. So let's go to the end. And if you look at the spectrum, there is no oxygen. But for some reason, we're still getting 10%. This is one of the drawbacks of a smart background. This is one of the only situations where the smart background doesn't work so well. What you'll notice here is we have no oxygen peak. But a smart background is sitting on the very bottom of the noise and therefore integrating what's above it. And so the smart background is overestimating how much oxygen we have left. So whenever you have a situation in the depth profile where you have a high signal at the beginning, like carbon or oxygen, and at the end it goes to 0, the smart background is not the best one to use. You're probably better off with a Shirley or a linear. Let's use a linear background instead. And now we end up with 0 oxygen as expected. So that's the only situation where a smart background doesn't work so well, where you have that disappearing signal. Okay, so that's the elemental profile, nice and easy. But what we really want to do, of course, is look at the chemistry. And again, this is where TFA or PCA can be helpful. So let's delete the tantalum peak. And again, start and end, TFA, smart background in this case, press start. So in this case, it's found 3 factors. But if you look at the profile that is generated from those 3 factors, it's all a bit noisy and nonsense, always like spikes. So let's try changing the signal to noise ratio up. There we go. So now we have 2 factors, oxide, metal. I changed it back to 3. Now, tantalum pentoxide is actually a bit tricky, of course, because the first level in green is pure oxide. But after we start sputtering it, it actually chemically is reduced by the ion bombardment. So let's leave it with the 3 factors here, except go back. And now we've plotted out some of the different chemistries. The TFA works quite well, but also PCA is a similar technique. So click on tantalum spectrum, put your cursors on, click PCA. Now PCA is a bit like TFA, except so TFA automatically works out how many factors to use. With PCA, we have to tell it. So let's say 3 factors and 3 factors, and click Analyze. So PCA is principal components analysis, and what PCA does, you may have come across it in other analytical techniques. PCA tries to find the mathematical functions which exist in the data. So TFA tries to find pure spectral shapes. PCA is similar, except it finds mathematical functions. And you see here where it's found. The red one is a pure metal, the green one's pure oxide, and the blue one is that damage which is caused by the ion beam sputtering. So what it shows us, this profile on the bottom right here, is the red one is the exact profile we would expect for the metal substrate. The green one is what we would expect for the oxide. The blue one shows that as soon as we begin sputtering, we end up damaging the oxide, and we actually end up with a lot of that as we profile. So again, the easiest way to process a profile is just to add the backgrounds, and that will get, in many cases, that will be enough. You'll generate an elemental profile. If you want to try and do some quick chemical analysis of your profiles, the TFA button in particular is particularly helpful for very, very quickly filtering that large number of spectra in a data set. Okay, so I think that's probably enough of hearing my voice. So I'll leave it there, and I'll answer any questions you may have. Otherwise, I'll pass back to James, and we'll bring it to a close.
Open up the questions again.
I have an easy question, probably an easy question.
Sure.
Just when you do the fit, what is the difference between fit, let's see, fit, the two fitting options, sorry. One is fit, fit or fit all? I don't have it in front.
Fit this or fit all levels, basically.
Yeah, fit this level or fit all levels. Thank you.
Sure.
Yeah. So so if you're looking at data like we were looking at the beginning, which is a data from a single point, then you would do fit this level. When you're looking at depth profiles or images, today we looked at TFA mainly, but it's also possible to actually do peak fitting for every level in a depth profile, for example. And in that case, you would use a fit all levels button. But before you use the fit all levels, you generally have to do a lot of work beforehand to set up your peak constraints, and then you do the fit all levels. But for a very quick process in the depth profile, the TFA can be more useful. It just as you see, with a few button clicks, you can actually pull out a lot of chemical information for very little effort.
And within the peak fit table, there actually is another button there that says flow the constraints through all levels. So essentially, it can get very tricky because you'll have to have constraints that will work for the beginning and the end. And sometimes that's very tricky to make sure that you've got constraints that will work for both the beginning and the end. So that takes a lot of pre-thought and seeing how it flows through. And then clicking the fit all button for the computer to do fit for every then single spectra. That's a fun day.
Is there
I'll defer.
is there an easy way to just set your depth profile so that it is looking at the actual depth?
No.
Yeah.
The simple answer is no. The sputter rate is not an empirically known value.
Mhm.
There is a calculator in the system that sort of references to tantalum pentoxide, but that's sort of the only known value. Every material will react differently to the ion beam.
Okay.
So if you want to do that, you can set an etch rate that will convert that,
Sure.
but you have to have an
Data.
external measurement to calculate it.
Okay.
So either you have a film where you know the thickness beforehand, or then you take your sputter crater, bring it to something else that can measure how deep it was.
Yeah, so if you do know what the thickness is, then you can just go to profile, time to depth, and you can either type in the etch rate if you know it, or like here, we know it's 30 nanometers. So it's 30 nanometers, and it took 700 seconds to get to the interface. And then click OK, and it converts it to a depth scale. As James says, you generally need to know what it is. That's one of the most common questions we have, and unfortunately with ion profiling, there are so many ifs and buts and caveats. It's not always easy to do.
One interesting possibility that will work for some systems is if you go through the help file, we didn't get a chance to cover today, there is a utility called single overlayer thickness, where you can use certain properties of a film. If you have a film where you can see the substrate signal through the film. And you know the properties of the film, like its density and some electronic properties. You can estimate the thickness of the film by the attenuation of the substrate signal. And so if you have a well-known film that you're sputtering through, as you get near the end, you can start seeing the substrate through that. So now you can start estimating the remaining film thickness to get back at the sputter rate. It's a thing in the software. There is in the help file, there is a description of it. Once you-
Layer thickness.
Is that what it's called, Paul?
Should I say again?
Is it actually called single overlayer thickness? Did I remember that correctly?
Single overlay thickness. Yes, that's correct.
Yeah. Yeah, look through that help file, to see how you play with that. And that's another way of getting a real number. Go ahead.
The data tables,
Mhm.
is there a quick and easy way to download all of those? Like say you generated a batch and you have a lot of data, or do you have to go to like every individual one and?
She's asking the best way to export multiple plots
Yeah.
like you have on the screen here.
Let me show you quickly again. So if you open up Excel, for example. So different ways of doing it here, but let's say we want to dump all the tantalum spectra. So display modes, here's a 2D chart, for example, copy, paste. That'll take all of the data straight out to Excel. Is that the kind of thing you mean?
Or do you mean the depth profile plots?
Either one is, yeah, that's good. Well, I still have to figure out how to do that without.
Well, I think if you go back to the data processing, if you export the entire window to Excel, I believe it'll do it for all of those. Yeah, if you export this processing window, this particular
Oh, the
processing window.
whole thing.
Yeah.
Yeah. So if you want to export the whole thing, yeah. So go to the reporting tab, and then report options, and then MS Excel options, and you basically tell it where to dump the data. So if you put it in here, for example. So it's going to put the data here. That's okay. Then select everything, and then select a style for the picture. So image large is a good one. Press the Excel button and report to that test one we just created. It will dump all of that data into a single Excel file, for example. So then you have the profile, the raw data itself, that sort of thing. Is that what you mean?
That's exactly what I mean. Thank you.
So hopefully, if James is still recording, then you'll be able to go back and watch that again just to see,
I'm hoping
how.
I am recording. I hope it actually gives me a video file. I haven't seen the first one yet.
Okay.
All right.
Does the software?
Yeah.
Does it have any ability to consider the nature of the sample? Like, so say it's nanoparticles versus just a very well defined thin film, or if it's like a or shell nanoparticle, as far as how the data would
Not
change in those different morphologies.
not within the software itself. Paul, did you hear that?
I did. No, and to create models for specific systems is beyond the scope of the software. So I know, for example, in literature, there's been some work on nanoparticle systems, but the amount of effort that has to go into a particular type of system is phenomenal. And then generally only really works when you have samples that fit those boundary conditions so well anyway. So that they're only true for a very narrow cross section. The main reason you do that often is to look at, if you look at like film thickness, then for nanoparticles you do have to treat the data differently to if you have just layers upon layers of films, for example. But for stuff like depth profiling and quantification, the XPS result is always averaged over hundreds of microns anyway, or tens of microns anyway. So I don't think in those cases it would be so helpful anyway.
I have a question, James and Paul, if you can hear me.
Yep.
When you did the montage, this is Mike Platic here from URI, by the way. When you do the montage, is there a way to get the resolution better on the scale bars, the axis? Because when you pull that up, when I've done it at my instrument, it's, you cannot really see the X and Y scales very well.
Let me reshare the software. Sorry, so how do you mean? So if you talk about
Or if you go under display modes
yeah.
and you go up to montage, I guess the fourth one there, or that one there, I think 3D.
Oh yeah.
So if you look at the X and Y scale, I have had difficulty when I try to put that into a report to get it to the point where it can be nicely viewed.
I must confess, I don't use montages too much. It might be a little bit different now. With version 6, is there a font control?
Yes.
Yeah, you could try maybe changing the font size.
Okay.
I think unfortunately the nature of, particularly in version 5, I think the nature of the display engine, it does look pretty ropey, doesn't it? But in version 6, I haven't tried that yet. But I think the only control you have is the font size and the font type.
Okay. And that was, where was that at again? When you
Yeah.
pulled
So the button says chart properties.
Okay, chart properties. Okay, gotcha.
Then axes, and then scroll along till you get to font.
Okay. All right, thank you.
All right. I think everyone here at Harvard is good. I think Mike's good.
Yep.
So Paul, we will leave you to your evening. And thank you very much.
Thank you, everyone. Have a good day.
All right, bye guys.
Bye.